All right, we do have some stats to do today. This is hard with only two monitors. I have so many windows. I'm like, where's this one? Where's that one? It'd be nice if I actually had another monitor. Oh well. Chi-squared, ladies and gentlemen. Chi-squared. There are 3 chi-squared scenarios. We've done the goodness of fit, and you watched a little bit about homogeneity. So we're going to continue homogeneity today, and then your video, and next time we'll talk a bit more about independence, okay? Thankfully, the math is pretty much the same for most of these. The GOF is a little bit different, but the math is pretty much the same for all of them, which is nice. We just have to still keep the 3 scenarios in our head and know which one is which, mostly for that, the plan stage. When you say, which procedure are you doing? You can't call a homogeneity test a GOF. Even though you might get the same answer, your interpretation's a bit different and the wording's a bit off. So the main hurdle is keeping these 3 things separate, straight, and which one is which. So we'll do the whole 4-step procedure here for the GOF, or for the homogeneity, and just make note of the slight differences, okay? And there's not that many of them. Your video, the test for independence, and your online homework. It's all online. The video and the homework is posted, but I haven't put it in a Teams assignment, have I? Make sure I do that at the end of class. It's on the website, and it's on YouTube, and it's on the sapling, but I haven't made it a Teams assignment yet. I forgot to do that this morning. Oops. All right. Mental note. So let's remind ourselves the difference between these 3. Okay, the first one we did was the GOF. This is the one that's a bit more different than the others. You have less chance of getting it confused with the other ones because you get a one-way table. It's just one row, essentially, a one-way table. And you're seeing, does your one sample, it's kind of a cool marker, isn't it? Does your sample fit your expected values? You have one sample, you have one categorical variable. Does it fit what you expected? All right, as opposed to what we are doing right now for today with the chi-squared test for homogeneity. Now, these 2 are the ones that are very easy to get confused. All right, here's where we really got to write, all right, which one is which? Because the math is identical for these 2. All right, the math is identical. They both kind of look like two-way tables. And so you can't really tell which one to do by the numbers. You have to look at the question and the scenario. So in a chi-squared test for homogeneity, you're asking yourself, hey, are these 2 populations the same? You're looking at multiple populations and saying, hey, is this variable distributed the same in these multiple populations? So is this variable distributed the same in these multiple, 2 or more populations? So sometimes you're helped out with geography. You're comparing the US to like Australia, or the US to Russia, or something like that. And you can tell, hey, I got a population over here, I got a population over here. Are they the same? It's not always quite that cut and dry, but in one way, shape, or form, you've got multiple populations. All right, as opposed to the one you're going to be doing in the video, where you have one sample. And you want to say, hey, in this sample, are these two variables related? All right, so I might say, are these variables, usually two variables, are these two variables related in this one population? Or if they're not related, then they would be independent. All right, knowing the one does not tell you anything about the other. There is no association. Or maybe there is an association, but you're looking for an association between two variables. Same math, but it was a different interpretation. But again, today we're doing this one, focusing on this one. But because it's the same math as the independence, your video is going to be nice and easy today. The math is the same, just a few slight differences in your interpretations, in your hypotheses, in your conclusion. Just a couple of phrases that are different. So let's do this real quick. We're going to just take a look at an example like usual, and then make note of a few changes here and there, okay? A few things to be aware of. So, would you vote for a female president? For a class project, Abby, Mia wanted to know if the gender of an interviewer could affect the responses to a survey question. The subject, does it create bias? The subjects in their experiment were 100 males from their school. Half the males were randomly assigned to be asked the question, would you vote for a female president, by a female interviewer? And the other half of the males were asked the same question by a male interviewer. So does the gender of the interviewer affect the responses, is what they want to take a look. So here we've got the table of their results, okay? As you can see, we've got ourselves this what looks like a two-way table, right? It's not just one row of information. We've got the gender of the interviewer on the top, and then the answers along the side. And so this right here, we're treating it as one population. And this one we're treating as one population. All right, because we took all the people that were being interviewed by the male, that's one population. They have the same experience. And then we took all the subjects that were interviewed by the female interviewer. Two different populations. We want to see, is there a difference between them? The expected counts, they calculated the expected counts here for us. Yeah, let's talk about that one more time, right? You did that in the video, didn't you? But where did the 34.5 come from? Why are there 34.5 expected people to say yes from a male interviewer? You should have done that on the video, but that comes from, let's see, we had to do 50 times 69, and then divide that by 100, right? 50 times 69 divided by 100. That should give us the right number. Where is my calculator? Turn on. Why aren't you turning on? On. There it goes. It's just slow today. All right, 50 times 69 divided by 100. That is angry. 34.5. There we go. Now, of course, our calculator will do that whole thing for us, okay? So you do not have to do each one of those numbers by hand like that. It is important for you to know where those came from, but yeah, the calculator will do that for us here in a bit. All right, our hypotheses. A few important things to note here. So our null, there is no difference in the true distributions of response to this question when asked by a male interviewer and when asked by a female interviewer. And our alternative, there is a difference. So again, we got the equal to, not equal to kind of vibe that's how I understand it. No difference, difference. So what's our takeaway here? What do we want to try to model in other scenarios? Your null is always there is no difference in the distributions, in the true distributions. And of course, as always, then add context, right? There is no difference in the true distributions. Add the context. In the populations. And of course, for the populations, you also have to add context. So for the first one, what was there? The first one was the context for the distributions. Distributions of response to this question. Okay. In the populations, what were the populations? The people asked by a male interviewer and the people asked by a female interviewer. Those were our two populations. Okay. So the null is that there's no difference, and the alternative, essentially the same thing, but there is a difference in the distribution. Is a difference in the true distributions. Oh no. Did it freeze?
It's like freezing and unfreezing.
Freaking internet. I have noticed that the internet is slower now that all the sophomores and juniors are on campus.
Yeah, mine froze. Did you stop at distribution?
I did, yeah. No, I started cursing the sophomores.
They're gonna be like this.
They're what?
All Tuesdays. They're gonna be like this. All Tuesdays.
I think all the days, yeah, Tuesdays and Wednesdays. Now that we got more students, I think it's all just gonna be. Well, actually, is it just you all? Because you're both here. Did it freeze for some of you or get choppy for everybody else online? Maybe it's just our internet that's bad, or maybe it's the student network that's bad. Because I'm not on the student network.
Yeah, student network always sucks.
Let me know if it gets choppy, you all out there at home. Okay? And then maybe I can yell at the computer and that'll help or something. It makes me feel better. It went white for you. Whoa. Hopefully it comes back. Refresh, exit out. If you need to leave and come back, that's all good. Sometimes that helps. Alrighty. So that's one of the biggest differences right there, actually, is just the hypotheses, what we are actually testing. The math is pretty much exactly the same, right? We have a random condition. That's the same as always. We have a large counts condition. All right, all expected counts are greater than or equal to 5. That's the same as always. Ooh, we don't check the 10% condition, right? Because this is an experiment. We didn't actually take a random sample, so we don't need to do the 10% business. That's the same as always. I will make a quick note, though, that we don't see this because it's an experiment, but because we have multiple samples and multiple populations, usually for the random condition, we'll say that yes, we have independent random samples. All right, if this was not an experiment, we do have to add that word independent. Because we have multiple samples, they have to be independent of one another. If you'll remember, we had to add that word independent when we did all the 2 sample tests for a Z interval or a Z test or a T interval or a T test. All of those we had to have independent random samples because we had multiple samples. Same thing here, we have multiple samples, therefore they must be independent. That wasn't necessary in this case, though, because we didn't take samples. It was an experiment. We randomly assigned. But still, we've done that before. Hopefully, that sounds right. Maria, if it's an experiment, you have to add independent. No, not for the experiment. You add the word independent when you have multiple samples. If you have multiple populations and multiple samples, then they have to be independent of one another. Like, it wouldn't make sense to do 2 samples in the same classroom. Like, I couldn't get my class and take a random sample and then take another random sample from the same class. They're not independent. The math doesn't work there. 2 different classes, then you're onto something because they would hopefully be independent. Different countries, you're pretty safe. But yeah, the independent is when you have multiple samples. All right, there's the conditions. Time to do the do. All right, where do we actually get these numbers? Okay. First, yes, the calculator will do all this for us, okay? It will give us the chi-squared number. It will give us the degrees of freedom. It will give us the p-value. And I'll show you how to do that right quick. That being said, a good test-taking strategy would be to actually write out the first couple of terms of your chi-squared. Okay, I think I've said this before, but if not, if you type something into the calculator wrong, like you accidentally hit a 3 instead of a 2 or something like that, your number will be off. And you get it all wrong then, because you just have the wrong number, the grader has no idea why you have the wrong number, and they have to mark it wrong. Whereas if you write the first couple of terms, they're like, oh yeah, they know what they're doing. Oh, their number's a little bit off. Yeah, but they knew that they were doing. They obviously were doing a chi-squared test correctly. You can at least get some partial credit, okay? That definitely helps Bolt's ego, okay? So, do you need to do this and write out the first couple of steps? No. It could be a good idea, though, to stay safe. Always good to practice safe statistics, all right? Where the heck do those numbers come from? It's the observed minus the expected. Observed minus the expected divided by the expected. So you'd go up to your tables. You'd take the observed 30 minus the expected 34.5 divided by 34.5. Oh, with the square, right? You square it, right? It's observed minus expected squared to get rid of the negatives, then divide by the expected. And then you do it again. Doesn't matter which one you do next. the order doesn't matter because you're just adding them anyways. So you could take 8 minus 5.5 squared divided by 5.5. And do 2 or 3, and then just put the dot, 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 and they'll hopefully throw you some points if you accidentally type it into the calculator wrong, okay? But, of course, it's best just to type it into the calculator correctly. It's not that hard to check your numbers. So let's do it. We all brought our calculators, right? We got our calculators. Pull those bad boys out. Someone at home's like, I forgot my calculator. Oh, wait. I'm at home. Ah! All right, watch. It's being recorded, so you can watch it later if you need. But I'll do them at the same time here on both calculators. So we got to type in this table, this 2 by 2 or 2 by 3 table. We have to type it into the calculator, and that's in a different place. You can't put it in the lists. The lists don't quite work this way. We're going to type it into a matrice, into matrix. Okay, we're going to change the matrix. So you're going to go second matrix right here. Okay, second matrix. On the Casio, it is the first menu item. If you go menu, it says run dash matrix. That's where you want to go. And then F3 is matrice. I don't know what VCT stands for, but you can let me know if you ever figure it out. And then matrix A is probably where you want to go. So on the Casio, you just select matrix A. On the 84, you have to go over to edit. You want to edit matrix A. Okay. On the Casio, let me delete it. So you see, on the Casio, you have to tell it what size you're doing. So when you hit enter on matrix, it asks, hey, dimensions, M by N. And you're like, all right, which one's the rows? Which one's the columns? If you forget, just flip them because it'll be obvious. Oh, that's not the right size. I can't plug my numbers in. So it is rows, then columns, I think, technically. But I always forget. And if you forget, it's not that big a deal. So it's going to be 3 by 2. If you mess it up, if you accidentally go 2 by 3, you'll be like, oh, wait, I can't type my data in that way. I better change them. So 3, by 2, and then you can type your data in. So let's scroll up here. There's our data. We type in the observed. So 30, and 39, 8, 3, 12, and 8. 30, 39, 8, 12, 8. So first thing, you got to type in the table. You don't need to put in the totals. Yeah, I could see that as being an issue. Yeah, we don't type in the totals, just the counts from the data. Just the counts from the data, not the totals. Just the counts from the data. All right. Once we've got that in there, you can probably guess where we're going to go. We need to do a chi-squared test. So we're going to go to where we've been going for the last month and a half or something like that, right? Tests, and then find chi-squared. This one just the generic chi-squared. All right, the chi-squared test for homogeneity and for independence are mathematically the same. And so that's why it doesn't say chi-squared test for homogeneity. To the calculator, it doesn't care.
Do we go on stats?
Yeah, stats, then tests. Stats, then test. Yep. And then same thing on the Casio. You go stats, test, chi, and then the two-way table is the one you want. The two-way right there. So it asks, hey, where are the observed? We put them in matrix A. If you chose something other than matrix A, you've got to put something else there besides matrix A. But I just put them in A, and that will make things easy on you. The expected values. So here's a nice thing. It's going to do that for you. So it's not asking you where they are. It's asking you where do you want it to put them. So it doesn't really matter what you put there, just so you know what's there. So we're going to go looking for the expected values in matrix B. And then you can either calculate or draw, whichever one you like. I'm going to do calculate, excuse me, this time. And so now we have our chi-squared, our p-value, and the degrees of freedom. Done and done. Not too bad. So 0.119. So the degrees of freedom were 2. Our p-value was 0.119. And our chi-squared was 4.25-ish. Done and done. Now, if we were doing this for real, we would need the expected values, right? Because usually you're not given the expected values. So when we would do the large counts, well, how would we do the large counts? Well, you'd run the test first. It would tell you the expected values. Then you can check to see if the expected values are actually all bigger than 5. And so to do that, we got to go back to matrix B. So second matrix, menu, home, run matrix, F3, go to matrix B. Now on the 84, I recommend go over to edit and then go down to B. That way you can actually see the numbers. And if you take a look here, you can now see all our expected values. And they all are larger than 5. So what can I do for you?
I got your desk.
Sweet.
Do you want me to just bring it in and then you can do your, because it looks like you got a little
Yeah, I'll have quite a bit of setup. If you guys want to set it here, maybe this afternoon I'll set it up, and then you just want to come and grab this one whenever you.
tomorrow morning.
Awesome.
Does that work? Okay,
Perfect.
sounds good.
Thanks, man.
Getting a new desk.
New desk. I'm excited. It's like Christmas. What if it's like exactly the same as the loaner I got? It's just like newer metal. It'll still be fun. Maybe these drawers are kind of sticky and a little iffy. We'll see. New desk. Sweet. All right, so yeah, here's where all our expected values came from, okay? They're all bigger than 10, so we're good. We can go on, but that's how you kind of have to go backwards a step then. It's not that big a deal.
So matrix B is like the expected values?
Yeah, it's the expected values then. Once you run the test.
Okay.
Yeah, once you run the test, then the expected values get thrown into matrix B. And I guess if one of the expected values was less than 5, they'd be like, oh, crap. One of them was less than 5. I shouldn't have done that kind of thing. But that way you don't have to do them all by hand. Let's see. Anything else I got to say? Oh, the degrees of freedom. I should say something about the degrees of freedom. Where the heck did the 2 come from? So here's the equation for degrees of freedom. All right, you take the rows minus 1, and you multiply that by the columns minus 1, and that gives you your degrees of freedom. So in this case, we had 3 rows, and we had 2 columns, not counting the totals, And so that becomes 2 times 1. Do you ever have to do that by hand? I don't know, but there it is. Why the heck is it like that? Let's take a minute and talk about that. You're all paying close attention, right? This is riveting, I know, just riveting. You're just on the edge of your seat right now, aren't you? All right, well, the degrees of freedom are so weird, but essentially, there only 2 values are free to move. Only 2 values are free to change. They have freedom They can be variables. Because as soon as those two numbers are locked in, well, now I can calculate the 12 because it has to add up to 50. I can now just subtract and figure out that one is 12. Same way, because the total here has to be 69, I can now calculate the 39 just by subtracting. Because this one has a total of 11, I can now calculate the 3, and I can now also calculate the 8, because, well, in two directions, right? Horizontally or vertically for the totals. So really, only two numbers were free to be variables. After that, everything's kind of set in stone. That's why it has 2 degrees of freedom. What's the test called? Where was it? The chi-squared test for homogeneity. I may or may not be pronouncing that correctly, not gonna lie. I think I have heard it pronounced in different ways. I think they put the emphasis in a different place. Homogeneity. I think I've also heard it called homogeneity. Thankfully, you don't have to say it. I'm just saying, right? You just have to write it. I don't. For me, it's easier to say homogeneity, but it is coming from the word homogeneous, I think. I haven't, no, because I haven't searched it up because I don't want to know that I'm wrong or not. It's best. I mean, ignorance is really bliss. It's best if I just don't know. In my defense, though, the guy I talked to this about, the stats teacher from Roosevelt, who's been doing this for years, he pronounces it homogeneity as well. So he's a little weird, not going to lie, but it's cool. But it does come from the word homogeneous, I think. The same. It's all that. Are these populations the same? All right, so that's degrees of freedom. I guess you might have a multiple choice question like this to use the, I could probably think of one, but otherwise your calculator reports it for you. So you may not ever actually have to do that. Who knows? It's not hard. And the last bit, the conclusion. The p-value is larger than alpha, so we fail to reject. This is all the same, I'm hoping, right? There is not convincing evidence of a difference in the true distributions of response to this question when asked by a male interviewer. That's just restating the alternative hypothesis. The structure here is the same that we've always done. I'm hoping that's not anything too crazy. It's greater than alpha, so we fail to reject. We do not have convincing evidence for the alternative. So if you wrote the alternative hypothesis correctly, you can hopefully just copy-paste the alternative hypothesis right here. There's no real difference. Okay, no real difference. We do not have convincing evidence for the alternative. Oh, and I guess I threw this in here because it's been a while since we've seen a p-value interpretation that's written well. Usually I just say, hey, remember what a p-value is? It's the probability of getting a sample like ours. I mean, that's a very simple understanding. It doesn't have all the pieces. So here's an interpretation that has all the pieces for your p-value interpretation. First, you assume the null is true. Assume the gender of the interviewer doesn't affect responses. You assume the null is true. And then it is the probability of observing differences in distributions. Well, that's the chi-squared. The probability of getting a chi-squared as large or larger. then those in this study as our sample by chance alone. It's been a while since we've seen a good sense for a p-value, but assuming the null is true, what is the probability of getting a chi-squared as large or larger as our sample by chance alone? And that probability is 0.119. So 12% essentially. 12%. Which is pretty big. That's a 12% chance. That's a substantial chance, which is why we failed to reject the null. It's like, yeah, that could have happened. I'm not super surprised that you saw this. It's not surprising, so we don't reject our original assumption, the null. All right, ladies and gents, before we practice this, any questions about that? Anything not make sense to you, that doesn't sound right, that you don't believe you could replicate? I do have some soda left. It's like, was that Gladiator? It might still be on Netflix if you haven't seen it. Great movie. Great movie. Gladiator. One of Russell Crowe's best, if I do say so myself. One of his best. Alrighty then, ladies and gentlemen. Time for us to practice this. See if you've got this. You say there's no questions, but I don't believe you. I don't believe you one bit. Nah, you'll be fine. This hopefully isn't going to be that bad. All right, so let me grab period 5. Whoa, computer, it's angry. It's saying, Bolt, state of the day, leave me alone. Why can't you just chill for a minute? I have no chill. That's what my students always tell me. You ever tell a teacher that? You have no chill. I've been told that in my day. Mostly by freshmen. Probably because I was yelling at them. Freaking freshmen. Teachers always say the freshmen these days are worse. That's always the thing. They always get worse. They always get worse. Oh, freshmen. They're not people. They really aren't. They really, really aren't. All right, I should not show that anymore. So now I can click on page 5 and start talking to y'all. Don't worry, it's not 5 different problems. It's basically just 2. All right, it's basically just 2. I'm not that mean. Oh, I guess I can stop recording, huh?